let's see. All right, so I'm going to switch to this thing. Here we go. I'm getting myself a new page. So on one side, let's see, I got red on the one side. Oh, I hit my elbow on that. So the whole thing is shaped like this. Erase this thing so it's open on the top. And I've got a tube. It goes like this. Like that. All right, so I started out with red water in here, and then blue water on this side. Well, that's like backward. Let's see. Blue on this side, red on this side, because I'm looking at it from the other direction. All right, so this side had hot water, and this side is cold water. The cold water is more dense, so it wants to fall down and head this way, and the hot water is less dense, and it heads in this direction. So we end up with hot water in the top tube, cold water in the bottom tube, and also we'll end up with a bunch of cold water that settles down here, and a bunch of hot water which ends up there. So how is this like the Earth itself? Well, if I draw the Earth as, I'll just draw like a circle, there's the Earth, and there's the core of the Earth, and the core of the Earth is hot. And then the surface of the Earth is relatively cool. So you have a relatively cold surface of the Earth. Just like how there's hot water in this right tube that's trying to go over to the left tube, this magma, the core of the Earth, is incredibly hot, molten rock. That hot molten rock wants to go toward where it happens to be cold. But in order for that rock to get to where it's cold, this cold water, the cool rock, has to go back toward the core of the Earth. What's a little bit more complicated is, in this demonstration, there's only like sort of one direction. It's a two-dimensional problem. The hot water goes up across this side, cold water goes down and goes back. The Earth is a sphere, though, so you have all this hot magma all trying to go to the outside, kind of all at the same time, but there also has to be cold rock to replace it. So what usually happens is this hot lava, when it gets to the surface, it splits and goes in different directions. And then the cool comes back. And then maybe somewhere else, you have hot magma that goes to the surface, and the cool comes back in two different directions. So like the Atlantic Ocean in the continental drift lab, you see like the Atlantic Ocean gets wider and wider and wider all the time. And that's because this crust on the surface of the Earth here and the crust on the surface of the Earth here, they're being like dragged along by the magma, which is in motion within the center of the Earth. So as magma rises from the core of the Earth and goes in this direction, it causes this plate to want to go that way. Similarly, as this magma rises up here and heads in this direction, it makes this plate want to go that way. And those plates move apart from each other. They separate. But then you get other places where those plates have to come together. So for instance, if I draw magma going up here, I get some going back like this, and some going this way. You'll also have a plate here and here that move together. So there are always plates moving apart. And a good example of that is the Atlantic Ocean spreading out wider and wider, and places where the plates move together. And a good example of that in the Earth's recent past, that's very fast, is like India moving north toward Asia and running into Asia. So all the while, the surface of the Earth has these plates which move around, and those plates are moved around almost like on a conveyor belt by the motion of this magma. Now, can we watch that happen? Like, can we actually see it happen? No, you can't like drill down on the Earth and cut away and see it. So all of this theory about continental drift and plate tectonics, we have a very, very, very good feeling about what is happening and why it's happening, because we observe things like how air mixes in how different temperatures of air mix in the atmosphere, how different temperatures of water mix in the ocean. And we also know, for instance, these places where that hot magma comes up, sometimes it doesn't just go underneath the Earth, it comes up on the surface. You get volcanoes. And the places where the greatest amount of volcanic activity happens is the places where these plates are moving relative to each other. And the places where there are no volcanoes, like we have no volcanoes in Pennsylvania. We also don't have earthquakes in Pennsylvania. We also aren't moving relative to other plates in Pennsylvania. We're kind of in the middle of one of these plates, which is kind of boring. But California lies along the boundary between the Pacific and the North American fault. They have frequent earthquakes. Earthquakes happen when these plates move and slide and bump up against each other. That's how we understand earthquakes. It's really hard to refute or say that this stuff is wrong. There's just so much evidence that shows that it's right. And it all comes about because of these differences in temperature. So what if the Earth was the same temperature the whole way? We want to get this motion. You know, continents would not move. They wouldn't move relative to each other. That's the big story. That's fundamentally like what's really taking place. That's a big story of the planet. That's a story that everyone should know. There's no reason why every human shouldn't know that to be true. Yeah. Yeah, good question. So eventually, like the Earth would have to cool down, right? This heat is generated by nuclear reactions. There's uranium within the Earth, which decays over time and generates a lot of heat. It's part of the mystery with the sun. So like, if the sun was actually just a chemical reaction, where like, wood is burning or something, the sun puts out an incredible amount of heat and it should burn through that fuel really fast. So it's not just a regular chemical reaction, it's a nuclear reaction. And it's the same with nuclear decay that happens within the core of the Earth. Eventually, the Earth will become the same temperature everywhere. And plate tectonics will stop, continental drift will stop, earthquakes will stop, volcanoes will stop, and erosion will take over. And it turns out that water will then cover the entire planet. Like, because what allows there to be holes in the ocean and mountains on land is the motion of these plates, and it's what allows land to be above water in the first place. So this Earth is a very dynamic place, and it's constantly in motion. Will that last forever? No. Is it going to stop in your lifetime? No. It's going to go on for a really long time. So there are different diagrams, and this is a diagram similar to one that's in your textbook, showing the different plates of the Earth. We live in the North American plate, which is actually connected to the South American plate. This big plate is all moving like as one thing. But then the African plate and Eurasian plate, these two plates are moving apart from each other. So the North American plate is moving to the west, the Eurasian plate is moving to the east. And at the same time, the Pacific plate, as it moves to the west, runs into the Philippine and Australian plate. And where those plates come together, well, two things can happen when plates come together. For instance, when the Indian and Eurasian plate come together, as India is going north into the Eurasian plate, it builds a mountain, like it goes up like this. The other thing that can happen, which we'll study, is plates can dive underneath each other. They go back to the middle of the Earth. So the western part of the Pacific plate, all of this ocean floor is actually going underneath the Australian and Philippine plate, and it's heading back to the core of the Earth. So like the seafloor here, it's heading back into the middle of the Earth, and it's being replaced by brand new lava that comes back up to the surface. Some plates are really small, some plates are large. The Eurasian plate is enormous, the Pacific plate is enormous, but then there are these small ones, the Easter plate, Juan Fernandez plate, they're very, very tiny because, things can kind of break up. So it's not a nice, consistent picture, but everywhere where there are earthquakes and volcanoes, those are places that happen like where the plate boundaries are. There's this thing we'll study called the Ring of Fire. The Ring of Fire is the area around the Pacific plate. The Pacific plate has the greatest amount of motion, where there's the greatest number of earthquakes and volcanoes all along the this plate boundary here and along this plate boundary here. In fact, about Japan is here. Japan has experienced frequent tsunamis, and those tsunamis are generated where these plates run into each other. So when plates move and crash into each other, that motion can cause a big disturbance in the ocean and create a big wave. It can go and just like take out a whole city, which is kind of exciting, also frightening. And along the west coast of the United States, there's lots of lots of earthquake activity because it's right along fault. So that's the big story. This shows the motion of those plates relative to each other. Some are moving apart, some are coming together, some are sliding alongside each other. And we'll study those particular kinds of plates. So the reason why we care about all this stuff about the motion of the plates is the place where the ocean is a place where the plates are like low, close to the center of the earth, and the deepest trenches in the ocean are at plate boundaries, places where there are volcanic islands, which then can create coral reefs. Those are around like plate boundaries or hotspots. Because another thing that you'll see on this map here, this Pacific plate is really big, but then in the middle of that plate, there's these orange spots, one up here, one down here. And those spots are also called hot spots because they're places in the middle of the plate where magma is also coming up to the surface and it pokes a hole in the middle of the plate. This is the Hawaiian island chain, and this is the Easter Island chain. And those island chains come up because magma comes up to the surface and it pops through the surface. It's kind of like a zit, which is kind of gross. So that's the big story. That's the story about like what's happening. Okay, in the study guide for chapter 2, I think it's like on the second page, you should know, because we'll use these terms from time to time, about basic types of rocks and minerals. Okay, so what the planet is made up of are rocks and also minerals. And I don't care so much that you know the difference between a rock and a mineral, but there's 3 different major ways that rocks and minerals are formed. Anytime a rock is formed because of volcanic eruption, it's called an igneous rock. So this word igneous rocks are rocks that form because of volcanic eruptions. I'll show you a couple of videos about Hawaii today. Hawaii will come up a bunch of times in the course because it's important for a lot of different reasons. But all of the rock in Hawaii is all igneous rock. It's all formed from volcano. They're big volcanoes that come up to the surface, form that type of rock. You don't find igneous rock here in Pennsylvania very much because it was in the far distant past that we ever had any volcanoes anywhere near around here. So they're important for the ocean. Another type of important rock are sedimentary rocks. And sedimentary rocks are the most common type of rock that you find in Pennsylvania. When you drive along a road that has rock cuts and you see those like layers that are like parallel to the ground, those are where sediment has been laid down. And typically on the ocean floor, where it's sand and like layers of coal are old, forests and rainforests where the vegetation has become compacted. So generally sedimentary rock forms in layers, and you see those layers oftentimes parallel with the ground, although they can get like tilted up and lifted up. But if you take an igneous or a sedimentary rock and you heat it up or increase the pressure over time, then that type of rock is called a metamorphic rock. So, things when we say metamorphic, like to morph means to change, and meta is like the same as, so it's the same type of mineral or rock, but it's changing. For instance, limestone, when it's heated and compressed, changes into marble. Shale, when heated up and compressed, changes into slate. And you don't have to know the names of those kind of rocks, but be aware that there's 3 different types of rock and mineral: igneous, sedimentary, and metamorphic. And because the middle of the earth, the core of the earth, is mostly made of like iron and nickel, a lot of lava is very rich in iron and nickel. And when it's exposed to the air, it rusts and changes to like a brown color and whatnot. Okay, so the specific terminology with igneous rocks. Let me do this. See if this works better. Yeah, I don't know why this is like overlaid. But this is a good example in this illustration of, kind of like a generic ocean. Here is a place where magma is coming up from the core and the mantle of the earth. So whenever rock is in the earth and it's molten, we call that magma. So magma is only molten rock in the mantle. If that molten rock gets to the surface, either underwater or on land, then you call it lava. So the name of the rock, or the name of the type of rock, we call it magma when it's in the earth and lava when it gets to the surface. So if you see a volcanic vent and the lava is coming out, it's true to call that lava. But when it's under the earth, we just call it magma. But no matter what, when that lava cools, it always forms an igneous rock, a rock that's made of magma that was from a volcano. And those volcanoes can be under the ocean. In fact, most volcanic activity is actually on the ocean floor. It's in the ocean. The middle of the Atlantic Ocean has this large mountain chain that's a long chain of volcanoes that's pretty much continuously erupting. There's places on the ocean floor where you can go down and watch the lava come out in real time and see that cool. So the lava doesn't have to get to the air. If the magma gets to the ocean floor and comes out into the water, then it's still called lava. Most of the ocean floor is an igneous rock that we call basalt. Let me see, I have a chunk up here. Here it is. I got a chunk of basalt. It just looks like a regular like black rock, but this rock is an ocean floor sample of basalt. And it's lava that has come up to the ocean floor base. As soon as it hits the water, it cools and forms this very, very dense rock structure. So most of the ocean floor is actually relatively boring basalt. So most of the ocean floor itself, since the ocean covers 70% of the earth, the ocean floor is the place where, we run into the planet. Most of the rock of the ocean floor is basalt. And that basalt can end up like up on land and whatnot, depending on how things move. And then because most lava has iron in it, it can have a magnetic field. And the most common mineral with a high amount of iron content that ends up storing this magnetic field is called magnetite. So magnetite is a specific mineral that we find all over the ocean, especially on the ocean floor, that when it cools will have the direction of the Earth's magnetic field locked into it. And that's what I want to show you some things about today. I guess that's about it for that. So anyway, there's in the folder for chapter 2, there's a PowerPoint slide deck that says Geomagnetism. And that's where these images are from. Both the images that I showed you on Monday about the basics ideas about the Earth has a magnetic field. The magnetic field changes direction and strength over time. And then the idea of the different plates and the motion of the magma in the Earth. And we'll come back to those maps as we go through the course. But in that slide deck, there's also links to videos. And I want to show some of those now. So actually, if you're remote, the best thing to do is if you go to chapter 2 and go to the plan for the week, it says plan for the week of 2/8 to 2/11. Then here it says Wednesday, February 10th. There are 3 videos here that describe magnetic mineral alignment, seafloor spreading, and magnetic reversal. And then why Hawaii's volcanoes are unusual. These are all excellent videos that show the motion of the magma and describe magma coming to the surface, ending up with a magnetic field and whatnot. All right, so if you're remote, the best thing to do is like not stay on the Zoom now, but go and watch those separately. I'm going to play them up on this screen for you guys here so you can see it and hear it pretty well. They're all really good. Let's see. One of them has a great YouTube channel called The Physics Girl. She does an excellent job describing all kinds of different physics stuff, not just physics, but geology, chemistry, all kinds of things. So if you're into science, the Physics Girl's channel is very good. Let me get to oceanography. I'm going to plug a speaker in. Where'd the speaker cord go? There it went. See, this thing's all like nice and purple everywhere now, except the bottom of this side is like just still blue all by itself because the cold water will settle down in there, and here the hot water like ends up mixing up, but this side always stays like smurf blue. And now it's all like consistent purple the whole way. Isn't that exciting? It's like one of the coolest visual illustrations of convection. Yeah, there's water in there warm now. Well, it'll end up like so to be honest, the water in the tubes is always pretty close to room temperature. The hot water heated up the one side maybe just by only a couple degrees, and the cold one didn't get that much colder. The water in the boxes is still like hot and cold, but the water in the middle is all pretty close to room temperature. Part of the issue is the tubes themselves are plastic, so the heat doesn't get conducted very quickly through the plastic. If the tubes were like metal, well, you wouldn't be able to see through, but it would like mix much faster. You know what I'm saying? So it doesn't take that much difference in temperature. And this mixing, you'll see like the time it takes for the magma to get from the center of the earth to their surface is not like a day or a week. It's on the order of thousands of years. So it goes really slowly. It's rock, but it's not really watery, and the difference in temperature is not that great. So the motion's very, very slow. Geologic time happens very slowly. So when we say a plate is moving real quick, in that illustrate in the continental drift lab, you see the Atlantic Ocean getting like a little bit wider, but that time scale is like tens of millions of years. So it isn't like we're flying away from each other. It takes a long time for the motion to happen. All right, let's see, plan for the week. I don't know if we'll be able to watch all of them this period, but I'll show you the rest next time. So this is the thing about magnetic striping on the seafloor.
No light except that made by the bizarre creatures within. There is no sound but the bubbling of hot sulphurous vents. It's a world that very few humans have ever set eyes on. And yet, this is a part of our world. We know less about the deep oceans of planet Earth than we do about outer space. The oceans are deep, dark, and full of mystery. Most of what we do know about them was only revealed in the last 60 years, when technology was finally able to see through the immense expanses of water. We now know that the ocean sits on top of oceanic crust, just as the familiar continents are fixed to continental crust. In the 1950s, a group of scientists became interested in the oceanic crust, and in particular, its magnetic properties. What they discovered changed how we understood not just the oceans, but the entire history of the Earth. I'm Ruth, and today I'm going to talk to you about magnetism at the bottom of the ocean. Consider a sailor's compass. The idea behind a compass is that it will always point northward, allowing the user to navigate across a featureless ocean. It is influenced by the magnetic field generated within Earth's core. Sailors have used compasses for many centuries. However, a compass can be influenced by forces other than the Earth's magnetic field. In the late 18th century, sailors from Iceland noticed local disturbances in the magnetic field that caused navigational errors. The disturbances were put down to magnetized rocks on the seabed around Iceland. In World War II, a new instrument was developed that could be placed on an airplane and used to detect submarines in the Atlantic Ocean. This device was a special kind of magnetometer, an instrument for measuring magnetic anomalies. After the war, it was modified and used to identify those disturbances the sailors had encountered. Planes flew back and forth across the Atlantic with magnetometers on board, creating a magnetic map of the seabed. Scientists knew that the rocks making up the oceanic crust were mostly volcanic, and they contained magnetite and other magnetic minerals. However, the scientists didn't expect them to form any particular pattern. Magnetic anomalies would be randomly distributed across the seabed, or so they thought. When the first magnetic surveys were finished, scientists were absolutely blown away. They did not expect what they actually saw: stripes of magnetic anomalies that switched between positive and negative. They saw a positive stripe next to a negative one, next to another positive one, and so on. What caused this pattern of magnetic stripes? It turns out that the Earth's magnetic field is not entirely static. It moves over time, which causes the north and south poles to drift slowly. Every few million years, it even flips around, so north and south are completely switched. When the rocks in the oceanic crust were formed, they preserved the direction of the magnetic field at that time. If it matches the direction of today's magnetic field, it can be measured as a positive anomaly. If the direction of the magnetic field is opposite, it can be measured as a negative anomaly. However, even this revelation doesn't explain the stripes on the seabed. To form stripes of alternating positive and negative anomalies, different parts of the seabed have had to form at different times. In fact, the whole seabed would have had to have moved over time. In the Atlantic Ocean, the magnetic stripes are symmetrical on either side of the mid-Atlantic ridge. Rocks on either side of the ridge have preserved the imprint of the current magnetic field and are geologically the youngest rocks in the Atlantic. As we look further away from the ridge, we observe the well-developed magnetic stripes. We can also see that the rocks get geologically older toward the eastern and western edges of the ocean. This model demonstrates how the seabed itself must have moved over time. The two strips of paper represent sections of oceanic crust that emerge from a mid-ocean ridge in the center. As molten rock is erupted at the mid-ocean ridge, it cools and solidifies, preserving the orientation of the Earth's magnetic field. Then the orientation changes. The magnetic field flips, and this change is recorded in the younger rocks. As more and more rocks are added in the center, the oceanic crust spreads further and further out. The magnetic stripes develop as the magnetic field keeps flipping back and forth. In the Atlantic Ocean, this whole process took 200 million years. It was very, very slow going. In order to produce the pattern of magnetic stripes that was discovered in the 1950s, the seafloor had to spread out. The Atlantic Ocean actually grew over 200 million years, and the continents on either side had to separate from each other. It sounds crazy, but this is the only reasonable explanation for how magnetic stripes were formed. Actually, that sounds a lot like Wegener's idea of continental drift, except it was given a new name: plate tectonics. Magnetic striping was a key piece of evidence in proving Wegener's ideas correct. Unfortunately, he didn't live long enough to experience the satisfaction of being right. Not only did the discovery give sailors the data they needed to correct their compass measurements, it also paved the way for a bold new scientific theory. Plate tectonics underpins our entire modern understanding of how the Earth works. It explains how volcanoes and earthquakes occur, how continents shift over time, and how the planet itself is developed. If you want to go back in time, studying plate tectonics is as close as it gets. The theory allows us to look back in time, reconstruct ancient continents and oceans, and visualize the prehistoric ecosystems that lived in them. Time is as deep as the ocean, and there is plenty of it still to explore. I hope you found this video helpful and you're keen to learn more. Thank you for
Okay, so a couple things. If you want to study the newest rock on the Earth, you go to the ocean floor. That's the place where the greatest amount of new rock is. So a couple of misconceptions. First off, the seafloor doesn't actually have a color like this, and the stripes aren't like visual. You know, it isn't like you go down and you're like, oh, I see visual stripes. And these stripes are on the order of hundreds of miles wide. But the point is that as magma comes up from the center of the Earth, this hot molten rock, it erupts through the ocean floor, what's called the mid-Atlantic ridge. And if right now, when that magma erupts, all this rock, whenever it cools along this line here for the newest rock, if north is that way, the rocks will have a magnetic field pointing north in that direction. What the blue illustrates is, at a period of time in the past, the Earth's magnetic field was opposite, where north was south and south was north. all of this blue, both to the west and to the east of that mid-Atlantic ridge, the widths of those halves are the same, and there's perfect symmetry on both sides. So these indicate periods of Earth's magnetic field reversal. This is like when south was that way, then north, then south, then north, then south, then north, then south. And she mentioned briefly in the video, this was accidentally discovered, totally accidental. Because in World War II, there was a big effort to try to like find enemy submarines underwater. One way to detect submarines is by, well, the fact that submarines are made out of metal, you can detect metal by detecting changes in magnetic field with magnetometers that fly overhead. So what they said is like, you'd have pilots who would be flying from east to west, and as they flew from east to west, the base level magnetic field readings of the Earth would change, and suddenly it'd be like north would be this way, and that's in alignment with the north magnetic field. They get to a place where all of a sudden the strength of that magnetic field would decrease. And that's because the Earth has a magnetic field in one direction, and the rocks have a magnetic field in the other direction. And it seemed like inexplicably, without explanation, there's these like lines of the ocean perfectly parallel to each other and symmetrical about the middle of the ocean where changes took place. So you could argue partly that if it wasn't for looking for submarines during World War II, trying to like do war, we wouldn't have accidentally discovered the fact that the direction of the magnetic field on the seafloor was different. And honestly, like this wasn't fully accepted until the 1970s, which is very new. Much of oceanography is brand new stuff, totally brand new, like completely brand new. Neither my dad nor my grandfather would have learned this in school because it was not known to exist. I'm an old hat, but they're even older. That's a good story. We consider that to be like absolutely certain. So you want to know how old something is, count those rings, those lines. It's much like if you cut down two trees, those trees have rings, and the rings show you annual growth rate. And if you have two trees that are 100 years old that grew near by each other, some rings are wide and some rings are narrow. And the width of the rings is going to be the same from tree to tree. Because some years the growing season is good and you get a real wide ring. Some years the growing season is bad, the rings are real narrow. It's the same thing on the ocean floor. You can find a pattern where it's like narrow, narrow, medium, wide, medium, medium, wide, super narrow, narrow. Those patterns repeat all over the planet. And so you can correlate ocean floor age and the rate of spreading based upon the widths. If the width of the stripe is real wide, the ocean was spreading real fast at that time. If the width of that stripe is real narrow, the ocean was spreading slowly at that time. That's the way in which we're able to develop those animations and find out about where the different continents were in the past. All that Continental Drift Lab stuff, those animations online, that's not just made up stuff. That's not just like, ooh, maybe the Earth looked like this. Maybe it was that long ago. It's by studying the patterns of those stripes in the ocean floor all over the planet. That's good science. The Earth is a dynamic place, and most of the Earth is covered in water, and most of those changes in the Earth happen either at shorelines or directly in the ocean itself. There's not a whole lot of new land made on land. It isn't like we got volcanoes in the middle of this country